take a look at the car parked in your driveway. You probably see a tool for getting to work, or maybe a monthly payment you regret. But that machine is just the tip of a massive invisible iceberg. The metal sitting on your pavement is the final receipt for the most expensive, complex, and borderline insane industrial projects in human history. We are not just talking about a new bumper design or a clever cup holder. We are talking about mega projects, billion-dollar gambles on entire systems that define how the world moves. From the obsessive precision of Japan to the brute force of American manufacturing, and from the physics-bending labs of Germany to the sheer speed of China, the automotive world burns cash at a rate that would make a small government blush. Manufacturers spend billions just to ensure your daily commuter starts every morning for 20 years without exploding. To understand how we got here and where your car actually comes from, we have to look past the dealership and onto the factory floor that changed everything. If you want to understand modern efficiency, you do not look at a clock, you look at the Toyota production system. This is the grandfather of every streamlined process in the modern world, built on two relentless philosophies: just-in-time and Kaizen, or continuous improvement. In a Toyota plant, there is no warehouse full of spare parts waiting to be used. That would be a waste of space and money. Instead, the exact alternator needed for a specific Corolla arrives at the assembly line mere minutes before the mechanic reaches for it. This is a high-wire act performed millions of times a day without a safety net. It requires a level of discipline that borders on the religious. If a delivery truck gets a flat tire 3 towns over, the entire factory line could grind to a halt. Yet Toyota pulls this off with such frightening consistency that they have become the gold standard for reliability. They operate with zero inventory buffers, meaning every single bolt and microchip must be perfect, because there is no backup in the bin behind it. It is a system designed to expose problems immediately so they can be fixed forever, rather than hidden under a pile of excess stock. Contrast this agonizing discipline with the new heavyweight champion of manufacturing chaos, Tesla. While Toyota spent 50 years perfecting the art of assembly, Tesla looked at the traditional factory and decided to rewrite the laws of physics. Their philosophy is defined by the Giga mindset, massive vertical integration, and the concept of the machine that builds the machine. The crown jewel of this approach is the Giga Press. For decades, the rear underbody of a car was a jigsaw puzzle of 70 different steel parts, all welded and glued together by an army of robots. Tesla replaced that entire swarm with one machine. The Giga Press is a house-sized aluminum die-casting monster that shoots molten metal into a mold to create the entire rear chassis as a single solid piece. It eliminates hundreds of robots, thousands of welds, and millions of potential rattles. It is an engineering audacity that terrified the rest of the industry because it prioritized speed and structural simplicity over traditional flexibility. The difference in risk profiles here is staggering. Toyota moves with slow, obsessive perfection, ensuring that a panel gap is measured in microns before the car ever leaves the drawing board. Tesla, by contrast, operates with a move fast and fix it later mentality. They will ship a car with a slightly misaligned trunk if it means the software architecture is 5 years ahead of the competition. It is a battle between mechanical perfection and digital speed. You might joke that a Toyota will run for 30 years, while a Tesla might arrive with a loose door handle, and you would not be entirely wrong. But that loose handle is attached to a chassis cast by the most advanced foundry on Earth. These two opposing philosophies are currently fighting for the soul of how cars are built. Toyota wants to refine the process until errors are mathematically impossible. Tesla wants to delete the process entirely and replace it with a giant specialized printer. Both are betting tens of billions of dollars that their way is the future. But building these machines is the easy part. Survive the torture of the real world, and that is where the money really burns. If you think the Nürburgring is just a racetrack where wealthy amateurs crash their Porsches on YouTube, you are missing the point. To the automotive industry, the green hell is not a racetrack. It is a dedicated industrial torture chamber. For 16 weeks every year, the track is closed to the public for the industry pool. During these sessions, manufacturers from Korea, America, and Japan ship their most secret prototypes halfway across the world, just to drive them in circles in the misty German mountains. It comes down to the brutal math of durability. Engineers have calculated that 1,000 miles driven at tempo on the Nürburgring is equivalent to roughly 10,000 miles of normal road abuse. It compresses time. A suspension component that might fail after 5 years of commuting in Ohio can be snapped in 2 weeks here. The track itself is a relic, a narrow, terrifying ribbon of asphalt, with blind crests and variable surfaces that no modern safety inspector would ever approve. That unpredictability is exactly why it is valuable. A computer simulation can model a perfect road, but it struggles to replicate the chaotic violence of a car bottoming out in the foxhole compression while cornering at 150 miles per hour. This physical violence exposes weaknesses that no wind tunnel could ever find, ensuring your wheel bearings do not disintegrate on the highway. While the chassis is getting beaten to death in Germany, the engine is undergoing an even more expensive evolution. We need to talk about the Formula One hybrid era. You might see F1 as a sport, but for manufacturers like Mercedes and Honda, it was the single most expensive engine research project in human history. When the sport switched to V6 turbo hybrids, it was not about saving fuel for the race cars. It was about solving a physics problem for the road. For a century, the internal combustion engine was horribly inefficient. A standard road car engine wastes about 70% of the energy in the fuel as heat and noise. It is effectively a heater that arguably moves you forward. The goal of the Formula One hybrid project was to break the 50% thermal efficiency barrier. To put that number in perspective, moving the needle of thermal efficiency by even 1% usually costs hundreds of millions in research. Jumping from 30 to 50% required re-engineering combustion itself. They spent billions developing systems like the MGU-K and MGU-H, complex motor generator units that harvest heat from the exhaust and kinetic energy from braking to spin the turbocharger and drive the wheels. This sounds like exotic race tech, but look at the hybrid system in a modern family sedan. The energy recovery technology that seamlessly switches your engine off at a stoplight and regenerates power when you coast was refined in the crucible of Formula One. The battery management software, keeping your grocery getter efficient, is a direct descendant of the systems used by Lewis Hamilton. It is a supreme irony that the technology driving a boring, sensible hybrid taxi likely cost billions of dollars to develop on the fastest race tracks on Earth. While engines were getting smarter, materials were getting lighter, and the infrastructure was getting complicated. If you look back at the BMW i3 and i8, it is easy to dismiss them as weird experiments. The i3 looked like an angry toaster, and the i8 was a supercar with the engine of a Mini Cooper. But viewing them as sales figures misses the point entirely. Project I was not just about building two cars. It was a billion-dollar lesson in material science that nearly bankrupted the accountants to please the engineers. BMW realized early on that batteries are heavy. To offset that weight, in 2013, you needed a chassis made of something lighter than steel and stronger than aluminum. You needed carbon fiber. But carbon fiber was slow, expensive, and reserved for Formula One cars. So BMW built a mega project to democratize it. They constructed a massive carbon fiber plant in Moses Lake, Washington, specifically to tap into cheap hydroelectric power because baking carbon fiber strands requires an obscene amount of electricity. They created a global supply chain where fibers were spun in America, shipped to Germany to be woven into mats, and then resin injected into chassis tubs in a process that took minutes instead of days. The financial brutality of this project was immense. They were trying to bring aerospace materials to a city car price point. While the i3 eventually faded, the lessons learned there taught the entire industry how to mass produce composites. They proved you could mass manufacture the future, even if the market was not quite ready to buy it yet. Every time you see a carbon roof on a standard M3 today, you are looking at the dividends of that massive initial gamble. But a lightweight car is just an expensive paperweight if you cannot power it. This brings us to the invisible mega project happening under our feet, the charging grid. We are currently in the middle of the largest infrastructure overhaul since the invention of the interstate highway system. We are not just plugging in toasters here, we are redesigning the electrical backbone of entire continents. There are two ways this is being built, and they represent the classic divide between closed perfection and open chaos. On one side, you have Tesla's supercharger network. This was a walled garden strategy. Tesla realized early that the car was useless if you could not drive it to grandma's house. So they spent billions digging trenches and laying copper before they had the sales volume to justify it. It was a vertically integrated bet: build the car, build the fuel pump, own the experience. It works because the car talks to the charger, the payment is automatic, and the reliability is high. On the other side, you have the open standard, the fragmented, frustrating world of third-party chargers. This is a chaotic mix of different companies, different apps, and broken screens. It highlights the sheer difficulty of coordinating a mega project when there is no single dictator running the show. You have utility companies, hardware suppliers, and software startups all trying to shake hands and often failing. The scale of power required is frightening. A truck stop of the future, with 50 semi-trucks charging simultaneously, requires as much power as a small town. We are digging up parking lots and upgrading substations at a pace that terrifies city planners. Infrastructure takes decades to build, unless you are willing to move at a speed that terrifies the rest of the world. This brings us to the sleeping giant that woke up and started sprinting. The Chinese new energy vehicle push is not just a car industry trend, it is a state-level mega project driven by sheer volume and vertical integration. If you want to visualize this, look at the port of Shanghai. It is a logistical machine moving millions of units annually, operating with a level of automation that makes other ports look like they are still using rowboats. For decades, China tried to catch up to the West in building internal combustion engines, but catching up to Mercedes or Toyota on engine refinement is nearly impossible when they have a 100-year head start. You cannot beat German physics or Japanese reliability overnight. So the Chinese government and automakers made a strategic decision: stop fighting the last war. They effectively bypassed the legacy of the combustion engine entirely to focus on the one thing that would matter next: the battery supply chain. By dominating the mining, refining, and production of batteries, brands like BYD flipped the script. They treat cars less like mechanical heirlooms and more like consumer electronics. A legacy automaker might take 48 months to develop a new car from scratch. Chinese manufacturers are doing it in 24 months. They are iterating models at the speed of smartphones. If a screen interface is laggy, the next version fixes it 6 months later. If a battery chemistry improves, it is in the car by next year. This smartphone on wheels philosophy fundamentally changes what a car is. In the West, we judge a car by its suspension damping and steering feel. In this new ecosystem, the car is judged by how well it integrates into your digital life. It is a rolling device. This speed allows them to flood the market with options at price points that seem mathematically impossible to Western executives. The geopolitical impact of this mega project is reshaping trade maps. We are seeing tariffs and trade barriers going up worldwide because established industries are realizing they cannot compete with this speed and scale on a level playing field. It is a harsh lesson in industrial momentum. Scale and speed can overcome a century of heritage if the technology shift is violent enough. While the West was debating the ethics of autonomy and the standards of charging plugs, the East built a vertical supply chain that owns the raw materials from the ground up to the battery pack in the floor. It is a gamble of unprecedented size. They bet the entire national automotive strategy on the idea that the internal combustion engine was a dead end, and they went all in on the alternative before anyone else was willing to commit. Now the rest of the world is scrambling to secure battery contracts while Shanghai keeps loading ships. So what does all this billion-dollar gambling actually get us? Whether it is the obsession of Japanese efficiency, the brute force of American casting, or the sheer velocity of Chinese manufacturing, these projects share one DNA: ambition. They define the absolute limits of what is possible. Look at your car again. That reliable machine in your driveway is the direct descendant of these billion-dollar gambles. It carries the invisible scars of Nürburgring torture tests and the brain power of Formula One hybrid research. It is funny, really. We sit inside these miracles of engineering, surrounded by 50 computers and composites born in hydro-powered labs, and we just complain that the seat heater takes too long to warm up in traffic. But as we master the hardware, the next mega project is invisible. With AI, the next great leap will not be about how a car is built, but who is driving it. Which feat impressed you the most? Let me know in the comments. If you need help choosing between the car you want and the car you need, watch this video next.